Okay, so this is the first AP problem on E6. This is a tricky one. It kind of takes the process of our rules and makes them backwards. Because rather than us trying to find something complicated out using rules, we know something complicated, and then we've got to kind of work backwards to figure out what the integral from 5 to 8 of g of x d of x is. So the thought process with a problem like this is that you actually kind of want to break this up into 3g of x, the integral of 3g of x plus the integral of 2. That's kind of the starting place because we can actually figure out what the integral of 2 is. We actually knew that from rules, but now that we have the fundamental theorem of calculus, we could just use that as well. So either way will work. When you're integrating a constant, you're just finding the area of a rectangle, right? And that's the thing. But the rules to integration work, so even if you don't remember that, it's relatively easy to do. So I'm going to rewrite the information that I was given here. So that's the integral from -2 to 8. I'm sorry, I'm not just going to rewrite it, but I'm going to break it up using my rules. So I'm going to take the 3 outside, and then I'm going to write the g of x dx, and I'm going to split it into a second integral, which is the integral from -2 to 8 of just 2 dx.
Oh, so you can make it multiple.
You can split addition and subtraction. Just like derivatives, they split with addition and subtraction. Integrals split with addition and subtraction. Just like derivatives, you can't do that when you've got multiply or divide. You can't just take, if you have a fraction, you can't just take the integral of the numerator, integral of the denominator. But addition and subtraction always works. And we know that because of our rules, that still equals 35. So now we're actually going to kind of do some algebra with this. We can't do anything with this right now. We don't have g of x, and we don't have integrals that go from, that split the interval -2 to 8. You know what I mean? We have 1. This splits the interval from -2 to 5, but then it's our job to find from 5 to 8. And just to add another level of annoyance to this problem, they have this one with the higher limit on bottom, which actually is we'll deal with when we get to. So there's lots of little things in this problem. But I don't have any way to figure out the integral from -2 to 8. The only way I would be if I had -2 to something, and then another integral that with that same something to 8. Or one of those integrals reversed, which we'll see in a minute how to deal with that, just to be extra annoying. But I can figure out the integral from -2 to 8 of 2d of x. It's a rectangle that has a height of 2 and a width of whatever the integral is here, which is 10. This answer is going to be 20, but if I forget that, I can use what we learned yesterday. What is the integral of 2 dx? 2x. Yep, 2x. So this is 2x evaluated from -2 to 8. This is still 3 times the integral from -2 to 8 of g of x dx. And this thing still equals 35. So without having to write it as a separate line, because I'd have to rewrite this thing again, that's going to be 2 times 8 minus 2 times -2. So that's going to be 16 minus 4. That's going to be 20, like I said it was going to be earlier. So now we have 3 times the integral of -2 to 8 of g of x dx plus 20 equals 35, which means that I can subtract 20 from both sides. Treat this just like it's 3x, but it's 3 times an integral. And I know that 3 times this integral equals 15. So 3 integral -2 to 8 g of x dx equals 15. So now I actually know what the integral equals. Because just like 3x equals 15, I can divide both sides by 3. So my integral, which no longer has a 3 over it, in front of it, integral from -2 to 8 of g of x equals 5. So now the three pieces of information that I have are almost exactly what I need. I have an interval from -2 to 8, and I have two subintervals, 5 to 8 and -2 to 5. So from -2 to 5 and then from 5 to 8, that is the full interval, -2 to 8. But they've given us one with the reverse limits. No big deal. This problem would have been just a hair simpler if rather than giving me this piece of information here, they had just given me the integral like I needed it, -2 to 5 g of x dx. But when you reverse the limits, what does that do to the answer? Yeah, it just changes its sign. It makes it negative. It's already negative, so it's going to bring it back to positive. Boom. So we can now get our answer basically just by writing, and I just like to just take it forward and then solve. So the entire interval, which is the integral from -2 to 8 of g of x dx, is equal to the integral from -2 to 5, which is the number that they gave me, of g of x dx, plus the rest of the way, -2 to 5 and then 5 to 8, g of x dx. And those are just numbers to plug in. 5, which is my full, equals the thing I don't know, plus 8. Not 8, 12, right? Sorry. I was looking at the upper limit. Wait, something's off here. Oh, it's this is the one that I know. So it's 12 plus this. Yep.
So we're getting the bigger interval and we're trying to find smaller.
Yep. Yeah. That's why I always, and there are other ways to do this. Like you could actually think it through on where your numbers need to go. But I always just like to write the bigger, to save myself from having to overthink something. Write the full interval on one side and put the subintervals being added on the other side. So 5 equals 12 plus, without having to write out a whole bunch of algebra, whatever this guy is. Obviously, it's -7. 7. So it's almost like you have to, this is an example of a problem where you have to like reverse yourself out of all of the stuff to get the simpler integral, rather than giving you the simpler integral and just straightforward asking you what something like that is. So like I feel like if that's a question that you can understand and do, there's nothing you can't do, at least in that realm. All right. Mikhail, your question. Number 14. And that's on, oh yeah, that's a little bit of a tricky one. That's on 7. Alrighty. Yep. So anytime you have to break up an absolute value into a piecewise function, you need to make a sign chart for what's inside those absolute values. So we have 1 minus x squared. You could do it just by thinking about it, or you can factor it out and just do it the long way. So I'll show the fact. I mean, you can kind of figure this out. When we get our answers, I don't think it's going to be that we're going to like, oh yeah, it kind of makes sense. But how would I factor 1 minus x squared? Factor. I want to factor 1 minus x squared. We're so used to we usually have x squared minus 1, and it's the exact same thing, except it's different. Well, that's x, but that's not what we have. Right, that's what we usually have, but this is 1 minus x squared.
Oh, it went.
Yeah, it's the x is this, so it's 1 plus x, 1 minus x. So we have, what we really have here is the absolute value of 1 plus x times 1 minus x. And then, to make the sign chart, you want the zeros of that, which are obviously 1 and -1, hopefully. And then we just have to decide when we're positive and when we're negative. Now, this is the one that's that's backwards because we have a minus x here. The 1 plus x should make sense. That's just x plus 1, 1 plus x. That's going to be negative before you hit positive 1. Or sorry, negative before you hit negative 1 and positive afterwards. So that's that. The 1 minus x is going to be the opposite way around. Its 0 is 1, and it's positive up until you hit 1. If you put something bigger than 1 into 1 minus x, that's going to turn you negative. So overall, where is 1 minus x squared negative? Right, yeah, so yeah, as long as you're not in the middle, so these are negative. So to turn this into a piecewise function, you're actually going to have 3 conditions. We're not going to need one of them because our integral is only from 0 to 5, but to turn 1 minus x squared piecewise, one of those conditions is going to be the same, but or 2 of those conditions are going to have the same result. If you're between negative 1 and 1, then you don't need to do anything to it. So it's just 1 minus x squared when negative 1 is less than or equal to x is less than or equal to 1. But on the other 2 pieces, you're going to be the negative version of that, which would be negative 1 plus x squared or x squared minus 1. And that's when x is less than negative 1, x is greater than 1. And my equal bars, if I could just as easily take the equal bar off of this positive 1 here and drop it down there. Because this is something that's continuous, it's going to be the same result either way. But I should only have it in one spot. So I figured I'd just drop them right in there and be done with it. So now I've got to integrate from 0 to 5, but I'm a piecewise function. So I've got to integrate from 0 to 1 and then from 1 to 5. So we have the integral from 0 to 1 of 1 minus x squared dx plus the integral from 1 to 5 of x squared minus 1. We're new, so the parentheses aren't mandatory, but they do help you see it. Not that they are parentheses, but the integral and the dx are what bind what you're integrating. So you absolutely don't need parentheses there, but we've only been doing this for a couple days, so I'll drop them in there just to be clear.
So would the integral mean anything different if you got rid of the dx? Like, I'm just kind of confused why that's there at all.
You can't, you need to know what you're integrating with respect to.
Gotcha.
Because you can, like, if we're brand new on this, but if you think, think back when we got to related rates, and all of a sudden we're like, hey, guess what? We can just start, differentiating with respect to anything. Now we're doing everything as a dt. So that really is there to tell you what you're integrating with respect to. In Calc 3, there'll be times where you'll have 2 integrals in a row, and then you'll have 2 different variables out here to integrate with. So it'll actually be like the outer one matches the outer D, and then the inner one matches the inner D. But that is way past AP Calc. So that dx is telling you what variable you're integrating with. And in that situation that I was talking about, like in later Calc, you would have x's and y's in this function. So it needs to be there. It is part of, it's telling you what to integrate with respect to. But we're only going to ever integrate with one variable. Okay. So following our antiderivatives, the antiderivative of 1 is x, and the antiderivative of x squared is, 1/3 x cubed, or I'm just going to write x cubed over 3. We've got to evaluate that from 0 to 1. And then not much different over here. It's the same 2 things with different signs. So we have x cubed over 3 again, minus x. I got ahead of myself in my brain there, and that's from 1 to 5. It's always great when 0 is one of your limits and you're working with polynomials because that turns everything into 0. So this first one becomes 1 minus 1/3, technically minus 0, plus 5 cubed. Yep, 125 thirds minus 5. I should be using my parentheses here. I think it's easier to keep track of everything you had to do because you need to have a subtraction for each evaluated at. So, and your function is 2 pieces long. So from there, I'm going to minus 1/3 minus 1. Sound good? So altogether we have, I'll just steal some space from the other problem. We have 2/3 minus 0, so 2/3 plus 125 thirds minus 1/3. I'm trying to get all the thirds together. And then I still need a minus 5 and a plus 1. Have I successfully not made any mistakes? I think so, yeah. So we end up with 126 thirds, which divides evenly. That's nice. And then we've got to, from that, subtract 4, combining the 5 and the 1. What does that look like? 42 minus 4? 120 divided by 3 is 40. So the extra 6 gives us 2, which is 38. Yeah. I mean, yeah. Sure. 15, I don't have it, so we can zip through it. I'll go on the quicker speed. All right, 15. So we're going from -1 to pi, so we've got to go from -1 to 0. Oh, sorry, which one did you want? 15, gotcha. Yep. Gotcha. I just did, yeah, you said a number and I didn't even listen to the number. I just looked at the other problem that was on the board. Yeah. We're actually going to do more of these today. That's actually really good to lead in. We're going to do these. Remember I kind of said we're thinking fundamental theorem of calculus here because that's the lesson we're on, but there are definitely different ways and better ways. I was about to say more better with the microphone on, so I stopped myself. So we've got f prime of x equals cosine x, and we know that the f of negative pi is 12, and we want to know what the f of 3 pi over 2 is. So the way we were doing this yesterday was we were basically writing the integral twice. Once we were doing it just by solving it, and the other way we were sort of writing out the fundamental theorem with our f's. So we need to take cosine x and integrate it from our 2 limits. So that's from negative pi all the way to 3 pi over 2. That feels long. And that's of cosine x dx. The integral of cosine is, the antiderivative of cosine is sine. Yep. So this is just sine evaluated from pi to 3 pi over 2. One of those is a 0, I'm pretty sure, right? The sine of pi is 0. Oh, it should be, yeah, yep. That's cool though, because the sine of negative pi is also still 0. Yep. So this ends up just equaling the sine of 3 pi over 2 minus 0. So I'm just going to write sine of 3 pi over 2 for space. And what do we have there? I think we have -1, right? Yeah. Cool. So, yep. But that integral, according to the fundamental theorem of calculus, any antiderivative can go where sine goes. So that's what we're doing next. So we're taking that same integral, and I'm probably writing out more than I need to. But again, there's also a better way to do this problem. Yep.
So when you're setting up the integral, you put the bigger number, like the f of the 3 pi over 2 on the top.
That's generally what we do, especially if you're the one in charge of making the integral. Yeah, absolutely. Lower limit to upper limit. This would all work as long as you stayed consistent. Because if you change those limits, you'd be writing things in a backward order here. If you had done it the other way, you would have gotten a positive 1 here. And then it would all still work out, but you know, unless you have a better reason to not do it that way, the better way to write the integral is with the upper limit on top.
So that simplified sine of 4 pi over 2, or?
This is 3 pi over 2.
Oh, because you're subtracting 0.
And then it's minus sine of negative pi, but that was just 0. And I was at my line, so I didn't write the minus 0. Yep.
Gotcha.
Cool. All right. So this, by the fundamental theorem of calculus, is any antiderivative evaluated at 3 pi over 2 minus that same antiderivative at f of negative pi. And we know that f is an antiderivative of it. So now plugging in what we know, -1 equals the thing we're trying to find out, and the numbers are so easy, I'll just write it this way. That number minus 12. Sound good? Yeah. And that sure sounds like 11 to me. Yep. Yeah, good. Good. And Andrew, this was the stuff that you were working on before too, but just presented in a different way. Like this is the one where you would start with 12 and then add the integral. So like that's why I said there's like definitely better ways to do this. This was just looking at it so if you just did 12 plus the integral from negative pi to 3 pi over 2, that would match what you were doing like 10 minutes ago.
So then, yeah, normal f is sine then? Oh.
Normal f is sine x plus c. We just don't know what the c is.
Dude, wait. It says f of negative pi is 12.
Mm-hmm.
So if that's sine of x.
This is what we're about to learn.
Yeah. So if that's 12, then how?
This is what f of x is. F of x is the sine of x plus some number that we don't know.
Oh, so that means.
Right. That means that's what we're going to do today. We're going to solve and say, hey, that c must be 12 then, right? Because you're saying to yourself, well, how the heck am I getting 12 out of sine, right? Exactly. You're not. You're getting 0 out of sine, but the c is 12. And that's how we're going to do it a third way today. We're going to get the function and then plug into the function. Okay.
X for 16.
No. Yeah, Mr. Bean does though. These are beans. Anytime it looks like that. So and we are going in order. This is beans 6.7. So.
And integral to sine 3x would be would it be negative cosine x over 3?
Yeah. No, negative cosine 3x. Remember, the argument never changes. Yeah. You might have been thinking that too. You just didn't say it. Cool. All right. Good thing it's a short one today. No, I did want to go over. Let me take it. Now I don't have a timestamp they can find it by fast forwarding. Okay. Indefinite integrals and differential equations. Okay. So we've been talking about definite integrals. We've been talking about antiderivatives. This first part is very, very little new. We keep calling them antiderivatives. More often than not, though, you really would call them an integral. They are a bit synonymous. You just have to be careful with the notation. The thing is, there are, like I said yesterday, there's lots of different functions that give you the same derivative. And the only difference between those functions is the constant value, right? I think I had x squared plus 100, and then x squared plus e to the pi. That's the only difference. So when we talk about an antiderivative, I don't care what you tell me, but an integral is a specific thing. And what we do is we tack on at the end of it a plus c. We call that c the constant of integration, and that's just the number that we don't know. It's the number that went away when we took the derivative. So when I ask you to find an indefinite integral, an integral without limits, I'm asking you to find an antiderivative, and then I'm asking you to write plus c at the end of it. That's basically what it comes down to. So this is exactly what we did yesterday. The antiderivative of x cubed is x to the 4th over 4. And the antiderivative of minus 4x is squared. Yeah, 2x squared. Good. And you were able to get the division and the simplification in your head. Awesome. But that is not what the integral equals. The integral equals that plus c. One of the things that they're super big on FRQs is that anytime you write an equal sign, the two things on both sides need to be equal. That integral does not equal just the algebra, or just the polynomial, I should say. It equals the polynomial plus c. So that is super important.
So let's
Yep.
try on D7. So for these answers to be correct in the A/B test, these would all have to have plus c at the end of them.
Depending on what the question said, because what did I was probably, so it said find an antiderivative. I don't know how much they're going to use the word antiderivative, because this is the test at the end. Like antiderivative is kind of a thing we use in the middle to just sort of, get to this spot. But I think if it's an integral, if you see that symbol, then you have to have the plus c. If they say antiderivative, yeah, and they can't mark it wrong if you don't have the plus c. You found an antiderivative, whether that c is there or not. Okay. Number 2, e to the 4x. We are reversing the what here? Linear chain rule. Just the linear chain rule. We'll wait till E9 to reverse the chain rule. So you'll be happy that you're. What's that? Well, the linear chain rule is made up, but the real chain rule is a real thing that requires a ridiculous process. Not ridiculous, but E9 is a 2-day lesson because reversing the chain rule is something that you need 2 days for. Reversing the linear chain rule, the thing that I made up, is simple because, obviously the antiderivative of E is E, but what do I need to do to it to actually get the correct answer? Over 4, yep, over 4 or 1/4. I don't know why I prefer the coefficient on E, but I do the fraction on the polynomial, but they are both correct. This could have just as easily been 1/4 x to the 4th. This could just as easily have been e to the 4x over 4. Cool. Number 3 and number 4, they're just examples of ones, because, am I right? I don't have an equal sign, so I guess I'm okay. What did I forget? The most important thing, plus c. The whole lesson is don't forget the plus c. So by number 2, I had already forgotten the plus c, so we're doing good. Number 3 and number 4 are just ones that you want to simplify first. We don't have a rule for quotients yet, but the whole thing is just over x. So I can separate that x and simplify to turn this integral into something I do know how to find the integral of. And that's, just going to be 3x, because the x cancels, plus 1 minus 2 over x. And then, of course, a dx. So again, the first 2 antiderivatives are relatively easy. This is going to give me 3x squared over 2. That's just going to give me plus x. And what's the integral of negative 2 over x? 2ln. 2ln absolute value of x. And if you want to know why, see yesterday's bubble that says y absolute value. And then, of course, the plus c. And then likewise with number 4, same deal. This is a product, so there's nothing that I can do directly with that product. But if I distribute that 3x in, I just have, I don't want to say a polynomial because I'll have a fractional power, but I'll have something that I can use the power rule on. So 3x times the square root of x is 3x to the 3 halves. 3 halves, yep. 1 plus a half. And then 3x times x squared is 3x cubed. dx, haven't forgotten that yet today. And then we can apply the power rule on that one. These are the ones that these 2 problems are the ones that you forget about, and then you see them and either you're like, I don't know what to do here. You try something ridiculously difficult to do, and then you realize, oh wait, I just had to simplify it first. Go for it.
Where did we get the 3 out of that? So we multiply that and it becomes
X to the first, x to the half.
Oh, right.
1 plus 1 half is 3 halves. We're just multiplying. We didn't do anything yet.
Okay.
We didn't integrate yet because we still have the integral symbol. So I should actually erase the integral symbol because now I am going to integrate. Oh, missed. Got it. So up the power by 1, so 3 halves becomes by 1 whole. So 2 over 2. 5 over 2. Yep. Means I have to divide by 5 over 2, which means I can multiply by 2/5. So I won't do too much without showing it. Plus, this is going to be 3x to the 4th over 4. So plus c, because it's an integral. And it's not equal if that plus c isn't there. So final answer, not much changes. 6/5. Why not? The square root of x to the 5th plus 3/4 x to the 4th. Questions on that? Yeah. Like I said, they're the ones that you're going to forget. Like this one, we're going to have so many things with quotients that you're going to see it, and for a second, for 10 minutes, who knows how long, you're going to just be like, what the heck? Oh shoot, I should have just split it up like that. Oh yeah, I should definitely drop my plus c there. Yep. So they're not all equal if that doesn't say plus c. So I always do a good job of forgetting to put my equal sign and the plus c. So hopefully I can plead my case, but I don't think you ever get to plead your case with an AP FRQ. But yeah. Okay. So here is a full list of integrals we know from our derivative rules. We saw some of these yesterday. Some of them are our cards. The derivative of x to the n is x to the n plus 1 over n plus 1, as long as n doesn't equal 1, and I remembered the slash that time. And then we do need to do plus c, because it is a derivative. The integral of a constant is just ax plus c. Correct. Yep. I remember the slash, forgot the negative. What do you want from me? To remember everything? This is my linear chain rule. That's why I have f prime there. The integral of f prime is always f, but since my argument is ax plus b, I've got to divide by a. So reversing the linear chain rule, I should say. That's just telling me I've got to divide. Buried in here is the fact that the antiderivative of f prime is f. And of course, that needs a plus c like the rest of them. Sine and cosine are each other. This time, integrating sine is what makes us negative. Working down the column, why not? It's easy. E to the x is e to the x. What gave us secant squared? Yep. This is nice. The rest, the negatives stay put. Did anything give us positive cosecant squared? No, but something gave us negative cosecant squared, and that thing was cotangent. But if you think about it, if I needed, to get rid of that negative, I need a negative over here. The derivative of negative cotangent x would be negative cosecant squared. So luckily with that association, the negative kind of holds. It's only sine and cosine that flip-flop. And if these are tan and cotangent, these must be secant and cosecant. Unless it's a test and I changed it up to try to trick you. But that's not my... If I was going to change something up, I would change the locations of both of them. Yes, and cosecant is negative, correct. Yep. All right. Let's avoid the elephant in the room and just drop down here to ln of absolute value of x plus c. This integral, a to the x, and this works for derivatives too. Like the reason that a to the x is what it is because you can turn it into e to the ln a of x. By the exponent rules, the first thing you would do to evaluate this would be to start by taking e and raising it to the ln a power, which would just give you the a, and then you're left with a to the x. So from there, you kind of see the linear chain rule in effect. You've got to treat this just like e, but you've got to divide by 1 over ln a. I need to put a dx here. So that equals 1 over ln a. Now I'm running out of room in my box, but then the next thing I should write would be e to the ln a of x, or ln a times x. But that, like I just said before, that's just a to the x. You don't need to know the middle. That's just how I remember it. I teach this today, and then maybe we see a problem in a couple weeks, and then the summer happens, and a new group of students are here, and I'm starting integrals, and I've got to remember, where the heck does that ln a go? So I just derive it for myself in my head, because I know how the derivations work. These guys all belong to the inverse functions, right? There's 6 inverse functions, but I only have 3 here. That's nice. I'm going to show you why. This one belongs to... Go ahead.
Plus C.
Oh, thank you. Yep. Yeah. Appreciate it. I'm going to forget plus C's. I'm going to forget DX's. You're going to forget plus C's. You're going to forget DX's. We're all in it together. What is that the derivative of? Made that a little bit.
The inverse.
It is inverse sine, yeah. Yep. That is the inverse of sine. Sine is the type of function that you can only get numbers, and this is how I remember it. Sine is the type of functions that you can only get numbers that range from negative 1 to 1, right? Look at what's the only thing that I can put in this. Negative 1 to 1. That's why, that's not why, but that matches sine, and it would have to match sine. So if that's one of my options, then that's the inverse sine. This guy must be then... No, cosine inverse is this guy with a negative 1 in front of it, which is why I don't have it listed. I'm going to show that when we get them all done, why I don't have a separate group here for cosine inverse and for all of the cos. We won't write the word co here. Okay, so let's look. We've got 2 left, and we've got a choice between secant and tangent. Which one's tangent?
Second. First one.
I'm assuming that we mean first one, second one, because this is the 0th one. I know. Yeah. Okay, so about no. This is tangent over here. All right. So we know we don't remember these. That's okay, because they are kind of obscure. You can get any number in the world out of tangent. The tangent function, there's an angle with a tangent of 1. There's an angle with a tangent of 1,000,000. There's an angle with the tangent of negative 1,000,000. There's an angle with the tangent of 0. Tangent does give you any number in the world, and you can plug any number in the world into 1 over 1 plus x squared. So same idea there. Secant, however, only gives you values that are bigger than 1 or smaller than negative 1. So secant only gives you improper fractions. That's a quick way of saying it. That is the ugly one for secant.
Tangent negative 1 gives you give it like a list of coordinates,
Mhm.
and it gives you the angle for that.
Yep.
What does secant give?
It gives you 1 over the cosine. So it gives you the reciprocal of the cosine. Yep. If you needed that, you'd be in a very specialized, there'd be a reason why you would need that, but that's what secant does. Yep, it gives you 1 over cosine. So now, like I said before, why don't I have 3 more of these with cotangent and all that other stuff in it? Well, here's the reason why. If I had given you the cotangent one, that would look like this. Negative 1 over 1 plus x squared dx. And I would put cotangent there, but I don't need it because that's not the way I would do this. I'd just pull the negative out to the front, and now I'd have the negative integral of 1 over 1 plus x squared dx, which means that this, which you could correctly write as inverse cotangent, is also negative tangent of x plus c. So that's why I don't have that there, because there's never a time where you need the cos. If you have a negative sign, pull it out of the integral and stick with the not co argument. It does turn out that the graph of cotangent of x, of inverse, this should see inverse. The graphs of tangent inverse of x and the graph of cotangent inverse of x, negative cotangent inverse of x, they're the same curve, just at different levels. So they end up, if you put in Desmos, if we had more time, maybe I would. Some other day we will. If you put tangent inverse in and negative cotangent inverse in, you're going to see the same shape at different levels. Go ahead.
Would it still be plus C or would it become minus C since you're multiplying it all by -1?
It doesn't matter because C is an arbitrary number. It would be a different C based on which one you wrote, cotangent or tangent. It's always okay to put plus C because we don't know what C is.
Right, because I was going to say, if C is equal to 5,
Yeah.
does that, like, plus C apply to the entire function, or does that plus C only get added after you take the antiderivative?
Well, because you're finding the function. You are finding the function, the specific function. So that plus C, that number you find is part of the function.
Okay,
Yep.
so I was going to say that integral, it's -1, which is equal to -1 multiplied by that integral.
Mhm.
So wouldn't it be tangent -1 of x minus C?
Yes and no. Yes and no. Because we don't know what C does, we don't need to worry about that. There's going to be ones where we'll see this in better, like later on. We'll definitely see. It's until we have it solved, we don't need to worry about constant multiples on it. So, if I'm multiplying the whole thing by -1, if you did that, if I wrote negative tan x plus C and you wrote negative tan x minus C, when we solved for our C's, we'd get the same number with opposite signs. Then when we plug them in, say I plugged in a positive number to my plus C, my result would say plus that positive number. Your result would say minus, but you would have gotten a negative number, so your result would say minus negative C, but that's just the same thing that I have, which is plus my positive C. Yeah.
Oh, that makes sense.
Yep. Yeah. I mean, you're definitely, it's something we're gonna have to worry about, but not today. All right. Because today, what we're gonna finish on are just the third look at these types of problems, the ones that we finished on with Mikhail's questions, and now kind of just seeing the process, the best way to do the problems. So these ones are in the context of I want to know what f is. I give you f prime, I want to know what f is. It's never enough just to ask those two pieces of information. You need at least one value of the function, because that plus c means that whatever curve you have could be at any level on the graph. But once you have one value of your function, that's enough for you to solve for c and find out what your function actually is. So let's take a look at how that works. When we have an equation of this form, which really just looks like we've presented a derivative, we call that a differential equation. So this is a differential equation, and I've given you a value of the function that we have the derivative of. I know that my derivative is this, and I know that my function, when I evaluate it at 0, is equal to 4. That's enough information to figure out completely what my function is. I'm going to integrate my derivative to get the function plus c. Then I'm going to plug in the information that I was given and solve for c. So I'm going to integrate f prime of x, which is going to be dx, which is going to be the integral of the f prime that I was given, e to the 2x minus 2x squared dx.
Can you say, and do you have to say that that's equal to f of x?
Probably, yeah, you definitely could. Yep. I might even have that on my notes, because I was really thinking when I was making them. Yep. Yeah, so let's do that. F of x is this integral, which is this integral, which we're going to get, and we're going to put a plus c on there. And because this is like so basic to calculus, we know what that plus c means. It means some number that we've yet to determine. So this function is going to be some algebra plus some number that we didn't determine. So all of our things connected by those equals are actually equal. Okay. E to the 2x is going to be e to the 2x, but I have to undo the linear chain rule. So over 2, yep. I resisted my urge to put the 1/2 out front. I don't think it matters. And then we're going to get negative 2x cubed, but over 3. We know that f of x is that, but we still don't know what f of x is because that c represents a constant that we don't know. So we're going to plug in, because we also know now the f of 0 is 4. So the f of 0 equals our function, which would be e to the 0 over 2, minus 2 times 0 cubed over 3, plus c, and that equals 4. And that's super easy because e to the 0 over 2 is 1/2. 2 times 0 divided by 3 is 0. So I'm just going to 0 it. 1/2 plus c equals 4. So c equals 3.5. Yep. Yeah, the sun's doing its thing again today. It's the same time as yesterday. Weird. Only shows up for 5 minutes every day. Okay, cool. I was looking at this. I was saying to myself, there's probably be a couple extra words here because they put it in dy dx form, but it's the same idea. A real problem would probably say that f is a function such that dy dx equals, but you get the idea for this example. The same thing. We're going to say that our f of x is the integral of 2 over x plus 6x squared, 6 over x squared, I should say, dx, which is 2 over x becomes 2 ln the absolute value of x. Yep. I know, and I hate saying it because it takes so many words to say it. 2 ln x, 2 ln absolute value. And then, of course, always careful. This is 6x to the negative second power. Question?
For the last one, it says like find the function like at the top, so like we have to rewrite that.
Smart thinking, yeah. Yep. Yes. Good call. Yeah, we did everything we needed to do except for actually write the function. So going back, the answer to this problem is the f of x equals e to the 2x over 2 minus 2x cubed over 3 plus 3.5. Which I did copy correctly, right? Okay, so we have 2 ln absolute value of x. We've got 6x to the negative second power. So we are going to increase that to over negative 1. But yeah, right, that's just going to, dividing by negative 1 is like multiplying by negative 1. It's just minus 6 x to the negative 1. I'll leave it there. I'll leave it there like that, especially because I'm plugging 1 into it. And then, of course, plus c. F of x is definitely equal to this integral, and that integral is definitely equal to this. So now we'll do the f of 1, which is just 2 ln of 1 minus 6 times 1 to the negative 1 power, which is just 1 plus c, and that equals negative 7. But the ln of 1 is, how about 0? The ln of e is 1, but the ln of 1 is 0.
Wait, what's the number to the negative first is 1.
Well, it is 1. The number 1 to any power is 1. Yeah. Yeah, right. Yeah, so it was nice. Any other number, I was spying ahead. Any other number, and I probably would have written 6 over x here. But I said, what the heck? I mean, it's plugging 1 into it, so yeah. Yep. I could even drop a negative 1 there. So we've got negative 6 plus c equals negative 7. So c must equal negative 1. Yep. I'm going to go counterclockwise here and look at number 4. What's that? Oh, thank you. I'm going to see if you guys are paying attention and not write the equation and wait for you to call me out on it, because that's totally what I was doing. 2 ln absolute value of x minus 6x to the negative 1 minus 1. number 3 is just, it ends up being a really easy one despite the fact that it looks disastrous. But we have f double prime this time. And we're actually given 2 conditions. Because we are going to integrate this twice. Every time we integrate, we're going to get a c. And every time we get a c, we need to figure out what that c is before we can move to the next step. So that's why we have 2 conditions. So we've got the f prime of theta. Oh boy, we use theta instead of x. Equals sine of theta. So we know that f prime single of theta is the integral of sine theta d theta.
That's just cosine theta, or wait, negative cosine theta.
Right? It's backwards of taking a derivative. Yeah, so it's negative cosine theta plus c. And since we know that the f prime of 0 is negative 1, that means that negative cosine of 0 plus c has to equal negative 1. And what's the cosine of 0? 1. So the negative cosine of 0 is negative 1. So I have negative 1 plus c is negative 1. So this c is 0. Yep. Boom. So it does turn out that in this case, the integral of sine theta d theta is actually just negative cosine theta. Which is nice because, and also not what I had in my notes at all, because I had a number here and then I had to, I switched to negative 4 and the negative 1 in my notes. That's what I did. Cool. I thought that felt weird. I should have looked harder. Okay, so now we'll do the same thing. So if now that we know f prime, it's negative cosine theta plus c, but c is 0, then f of theta is the integral of our new function, which is negative cosine theta d theta, which I wrote too high. And the integral of negative cosine is negative sine. Yep, so you've got negative sine theta, but plus c. And the f of 0 is negative 4. No, I usually leave some space. So the f of 0 is sine 0, negative sine 0 plus c.
Sine of 0 is 0.
Right, yep. And then that equals negative 4. But that's just 0, so I literally just have c equals negative 4. I'm there. I forgot to write the equation. So my f of x is negative sine theta minus 4. Make sense? Yeah. When I did it in my notes, I didn't get that middle c equals 0, so I actually ended up getting negative sine. When I integrated the next time, I had negative sine theta plus that coefficient times theta. I had like a whole different thing going on there, but yeah. I actually had 3 terms. Cool. All right. You know how to do it. You've seen everything you need to do it. This is just sort of a special case. I'll go through it quickly because we're not losing sleep over just this could have just as easily been a problem for you guys to try. Antiderivative, so f of x is the integral of 2x dx, 2 to the x dx, which is, as we saw before, 1 over ln 2, 2 to the x plus c. That's right from our derivatives on the front page, except we had a instead of 2. So the f of 1 is 2 to the 1 as my numerator. ln 2, I just moved the 2 to the numerator, plus c, and that equals what f of 1 equals, which happens to also have a 2 over ln 2 in it. Wild. Plus 5. So c equals 5. Again, that was quick. I get it. Don't let me not forget to write the thing. So f of x equals, where's my function? 1 over ln 2, 2 to the x plus 5. Awesome. That was a quick version. Hey guys, we'll see what happens next week. You guys all have both packets, right? Did you get both packets, Kaya?
Yes.
Okay, perfect. The thought is it is going to be the second day where we have a full class period after we come back. Yeah. There are, yeah, E8 and E9, just in case. In case we're virtual on either of the Monday or Tuesday of next week, which I feel like is a distinct possibility. That way you guys will have the paper if your name isn't Carter or Colin.
Alright, I'm trying to think of the whole book.
Cool.
I was always kind
You too, Mikhail.
every time I sit down, I have to like re-remember everything. That's why
That is how it works. Yeah, that is how it works. When are you going to take your quiz? Oh, good. Oh, sweet. When are you going to take your test?
I could come on Monday, either early or after school.
Okay. Okay, that'll work. Yeah, and I'm going to tutor whatever the first day is that we're
Okay.
here.
So either Monday
So yeah,
or Tuesday.
or Tuesday. Yeah. Yep. Yeah, I'll be here. And I'll be.
Oh yeah, because this week it was Wednesday, and I always drive my brother's school.
Oh, okay. Yeah.
Yeah.
This week was Wednesday. Yeah. So hopefully the first day of the week next week won't be Wednesday.
Yeah.
Well, actually,
I mean,
tutoring wouldn't be Wednesday next week because it's a half day.
Yeah, but.
So tutoring, I mean, if we're not here Monday and Tuesday, tutoring will be Thursday. Yep. All right. We'll see you. Have a good weekend.
the return of Ivan.
The return of Ivan. Let me stop recording, Ivan. I've got all my weird conversations preserved in
I never knew I grew